The next speaker, the next session is a good follow-on to our earlier topic, and the session is using SPDK to optimize the NVMe-OF Fabric's RDMA stack. We have two speakers, Seth and Alexey. Seth has been working for Intel since 2017 on SPDK project. He got his start working on continuous integration and automated testing for the project. Currently, much of his development time on NVMe-OF Fabric's feature development. He also manages library architecture and versioning of the project. Alexey is from Mellanox and is also on SPDK project. He's a member of SPDK core maintainers team. His area of interest in RDMA and NVMe over Fabrics optimization is what brings him here. Alexey also has experience in development of network protocols and in distributed machine learning. So Alexey, I'm going to find you guys in the audience and try to make you presenters. So just hold on a second. Yeah, there, Seth, try please.
Great. Can you hear me?
Yes, we can. Alexey, you're also able to, we can hear you if you try.
Hello, thank you for introduction.
Sure.
That will start the presentation.
All right, great. Well, thank you very much for the introduction. We're Alexey and myself are both very grateful for the Open Fabrics Alliance for putting this all together. It's definitely been an exciting experience so far. Next slide, please. Great. So I'll be kicking things off by talking about just briefly about the design goals of SPDK, specifically the NVMe over Fabrics module, as well as some of the primitives that we use within the NVMe over Fabrics module, both on the target and initiator side. Conceptually, some of this introduction is going to cover the same things that ZA's introduction did, but I'll try and touch on these topics in a bit of a unique way and possibly provide a different perspective that is still enriching. After that, we'll move on to some more enterprise features and performance optimizations that have been made to the NVMe over Fabrics module, some of them specifically to the RDMA transport. I'll be starting that off by talking about initiator side port failover, and then at that point I'll turn things over to Alexey to talk about performance optimizations as well as data integrity, including diff and DIC support. Okay, next slide, please. And one more. Great. So the storage performance development kit, for those of you that were in ZA's talk this morning, is an open source project. It has existed in its current state, that is being hosted on GitHub since 2015. It is a BSD licensed project. It is primarily a set of libraries for optimizing a storage stack. It also includes several applications based on those libraries, one of which is an NVMe over Fabrics target application. So when we talk about the NVMe over Fabrics module within SPDK, we are talking about those libraries, but there is also a standalone application that sits in the repository. Of course, since SPDK is a user space storage stack, it was ideal for NVMe over Fabrics, specifically the RDMA transport, which already allows for pinning of user space buffers and has a lot of the same design goals, limiting system call overhead and things like that. SPDK is also geared towards being completely lockless in the I/O path. When we were designing the NVMe over Fabrics module, we wanted it to be scalable, both in the number of connections that it could handle, as well as the number of both NVMe drives and network interfaces that the libraries could handle efficiently. Another hallmark of the SPDK NVMe over Fabrics module is that it has a simple and efficient transport plugin interface. And this is true at two different levels. The transport interface has been designed such that it is, in order to implement a new transport, one simply needs to fill out a function table and register that new transport with the generic layer using a constructor function. So that entire interface is hosted in a public header file. So it's actually possible to create and maintain out-of-tree modules that can plug in efficiently to the generic NVMe-over Fabrics layer. Currently, we have 3 transports in the NVMe-over Fabrics module that are hosted within the SPDK repository itself. Those are, of course, RDMA, TCP, and fiber channel. We also provide a secondary level of plugins. This is, of course, within the transport itself. We call it a provider plugin interface. So for TCP, this is essentially you can pick your socket abstraction, whether you want it to be POSIX, or for those of you that were in ZA's talk this morning, there's obviously the VPP or vector packet processing socket abstraction as well. For RDMA, this takes shape in the form of different hardware providers that have extended verbs options for specifying connections and things like that. And of course, as I mentioned, it is a BSD licensed product. So next slide, please. Great. Here I'm going to take a little bit more of a dive into some of the actual primitives and types associated with the NVMe-over Fabrics module, and these are going to be consistent between both the target and initiator. The key takeaway here is that the form of these primitives really fits with, the function of the target itself. There are 2 subsets of these primitives. The first one is globally available primitives. And these are going to be primitives that are accessible from every thread and core within the SPDK application itself. So these include both the subsystem, which is essentially the abstraction of the NVMe controllers and namespaces. These, of course, need to be accessible from every thread in the application so that you can fully utilize the system resources in order to maximize the number of connections, the amount of processing that you can do on each one of the individual NVMe devices. The transports are also, of course, globally available, and within a single SPDK application, you can run multiple transports from every single thread. So RDMA and fiber channel can exist concurrently in the same application. Now, in order to remain lockless in the I/O path, and this was touched on a little bit in ZA's talk earlier, there is a necessity to make sure that the base level, each connection is only accessed from a single thread. So in order to accomplish that, every single NVMe-over Fabrics queue pair is pinned to a specific SPDK thread. Now, I want to draw the distinction here. An SPDK thread is not a CPU core. There has been a decoupling of SPDK threads, which are lightweight threads, from CPU cores. So at connection time, the SPDK thread for a queue pair is fixed, but as loads go up and down, you're able to actually migrate SPDK threads between cores. If you're using the built-in SPDK NVMe-over Fabrics application, that currently doesn't have a load balancing feature built into it, but by leveraging the libraries directly, you can use the the SPDK thread feature to perform load balancing at that level. So that queue pair structure and abstraction, and the way we deal with that is how we maintain locklessness in the I/O path. In order to maintain scaling, we actually have a per thread pull group structure. It is divided into two parts. The first is the subsystem pull group, which is really a convenient structure that contains a per thread context of controller and namespace information. The second structure is the transport pull group, which contains the software abstraction necessary to actually communicate over the network transport. And luckily, in both RDMA and TCP, there are very ready structures that allow us to decrease the cost of adding more connections on a single thread. So for example, in TCP, we have the ePoll concept, which allows us to poll once and only perform work on queue pairs that actually have more data for us to process. And then in RDMA, this works in terms of a shared receive queue and shared submission queue. Every queue pair within a single poll group is going to share both of those data structures, which helps both with memory efficiency and reducing the number of calls into the actual librDMA. Next slide, please. And so here we're going to start getting into the performance optimizations, as well as, of course, some of the more enterprise features relating to failover and data integrity. The first one here that I'm going to go over is initiator-side multipath support. And this came about really out of the community when community members wanted to be able to efficiently fail over between multiple paths to the same namespaces without having to do a lot of work at the application level. So we introduced a couple of new APIs to assist with that. And if you'll turn your attention to the diagrams down below, it'll sort of helps explain this. The idea here is that you've got two NICs on the target side that are both connected to the set of drives. And then on the initiator side, you can imagine that you've already created a controller structure and have multiple NVMe queue pairs connected across to the target side. So all those software abstractions already exist, and they're working in the initiator side. But either because there's a failure in the networking somewhere, or simply, this for load balancing purposes, the software decides to shut down the NIC that you're currently attached to, a failure on that controller. So the changes that we made are when this failure occurs, instead of cleaning up that controller structure immediately on the initiator side, we've simply put it in a failed state where all the queue pairs still exist and the controller structure itself still exists. And we sort of pass it up to the application to decide what to do with it at that point. In the event that you have a second path on the target side that export those same namespaces, it's as simple as calling two API functions to complete this failover process. The first one is SPDK NVMe controller set TRID, which allows you to change the TRID is short for transport ID, which is essentially the IP address and port of the endpoint. So you're allowed to change that transport ID for the controller, and then call SPDK NVMe controller reset, which reinitializes that connection and allows you to get back to work on all of those queue pair structures and your controller. So this feature really allows for very quick recovery without having to sort of reinitialize and reconfigure everything on the initiator side when there's a network change on the target side. right, next slide, please. Great, thank you. And so with that, I'm going to turn the time over to Alexey to do a bit more of a deep dive into some of the RDMA performance features and diff and dict support.
Thank you, Seth. In my part of the presentation, I will cover two RDMA optimizations implemented in SPDK, data integrity problem, and hardware signature offload. Let's consider how NVMe-OF target handles IO read operation. When a target receives a read request from the initiator, it posts a command to NVMe disk to read data to a local memory buffer. When the disk finishes read operation, NVMe-OF target prepares and sends two work requests back to the initiator. The first request is the RDMA write, which transfers the data, and the second one is a send work request with the NVMe-OF response, which is used to notify the application that the operation is completed. These two work requests produce two work completions on the target, and since RDMA write and send operations were sent in a strict order, completions for them will be generated in the same order. That means that we can skip processing of RDMA write completion by marking this work request as non-signed and finalize operation in target during the processing of the send work request completion. This optimization reduces the number of PCI transactions, and the advantage is especially noticeable on ARM machines, where the number of IOPS can be increased up to 15%. Next slide, please. So typically, every IO operation requires posting of one or more send work requests and one receive work request. In most of the cases, work requests are posted independently, which causes frequent update of NIC durable register and produces extra PCI transactions. The idea of this optimization is to batch posting of work requests. Instead of posting individual work requests, we put it in a queue, and the queued work requests are posted together on periodic basis inside of special function which posts completion queue. And this allows to reduce the number of durable register updates and the number of PCI transactions. This optimization is especially effective in high IOPS cases, and as the previous optimization, the advantage is higher on ARM machines. For example, with QDEPS64 and for payload, the number of IOPS in read scenario increased up to 5%, and in write scenario up to 12%. Next slide, please. The next topic is a problem of data integrity. Okay. We will look at the effects of data errors and the necessity of their early detection. We will check which mechanisms are provided by NVMe specification to resolve this problem and what is implemented in SPDK. So why should we worry about data corruption? The obvious answer is that it is fatal to business logic. It may break your backups and do many other bad things. If we consider some user space application built on top of SPDK, then data might be corrupted in any element on its way to remote disk. It can be either SPDK NVMe driver or NIC or NVMe disk itself. Usually each of these elements performs its own data integrity check. For example, IP checksum is verified when data goes through the NIC, but each element may contain some bugs that can overlook the corrupted data. End-to-end data protection is a proactive error detection approach. It is used by NVMe specification. It relies on additional portion of data which is transferred together with main data block and contains information that can be used to catch data integrity errors. End-to-end mode allows to notify the application about errors occurred during I/O operation and prevents the use of corrupted data. Next slide, please. NVMe specification uses TIT&diff format to store protection information per data block. TIT&diff is a 8 bytes field where the first 2 bytes is a guard tag, which contains 3616 checksum covering data block. The next 2 bytes is the application tag, which is user-defined content. It's opaque for NVMe controller. And the last 4 bytes is a reference tag, which protects against misdirect block transfers. NVMe specification defines 3 protection information types, which are the properties of a namespace. And from NVMe point of view, they differ in content and usage of reference tag. Protection information can be transferred as a contiguous part of data block. And such combination of data and metadata is called extended LBA format. It is used in data integrity field or diff specification. And another approach is to transfer protection information as a separate buffer. It is used in data integrity extension or DIX, and it is not supported by NVMe-OF fabric specification. Next slide, please. This slide illustrates the principles of end-to-end data protection mode and the SPDK extension, which is called diff-insert-to-strip mode. In end-to-end mode, when the application starts write operation, it generates protection information according to TIT&diff format and stores it in metadata part of extended LBA. This extended LBA is transparently transferred through the network to remote NVF controller, and protection information is verified by NVMe disk before writing. In a read operation, the disk verifies stored protection information, and data block with metadata is transferred to the application, which performs verification on its side. If any of verifications failed, the application will receive a response with failure reason. In SPDK diff-insert-to-strip mode, metadata and protection information capabilities of namespace are hidden from the host. It sends or receives data blocks without metadata. And in write operation, when SPDK transport layer receives data buffer from the host, its transport layer generates and inserts protection information for each data block before writing data to the disk. In case of read operation, SPDK transport layer verifies protection information, strips it, and sets data blocks to the application. This mode is supported by TCP and RDMA transports. Next slide, please. The current implementation of SPDK diff-insert-to-strip mode uses software CFC16 calculation optimized by Intel ISID library. And this implementation has several limitations. The first one is that encapsulated data transfer is not supported, since it is impossible to insert metadata without additional memory copies. And encapsulated data transfer is a mechanism which allows the initiator to send data together with NVMe-OF capsule. It is used in write operation. And the second limitation is that this mode only supports protection information type 1, since the application doesn't provide reference and application tags, and SPDK manually sets them to some appropriate values. The advantage of this solution is that it works out of the box and can be used by applications which don't support metadata and protection information. The disadvantage is low performance due to software calculation and high CPU load. Also, this approach doesn't protect data blocks all the way from the initiator to the disk. Next slide, please. It is possible to apply hardware accelerations when data goes through the NIC. One of such accelerations is hardware offload of tit and diff calculation, and Mellanox is developing user space API to support it. The API treats signature as a property of memory layout. The API introduces a new special signature memory region, or SIGMR, which is built on top of a regular memory region. This SIGMR describes one IO transaction, and it consists of two domains, memory and via. These domains define where a signature should be calculated. For example, in our prototype of SPDK diff insert to strip mode with hardware float, we configure signature in memory domain. Each domain has protection information related properties such as application reference and guard tags, size of data, metadata location, and others. Using different combinations of wire and memory domains, we can enable various scenarios of verification, inserting or removing of protection information. It can also allow us to implement DIX mode in NVMe-OF by providing interleaved data and metadata buffers. When we use hardware signature offload, each IO operation requires to register SIGMR. To do it, we should prepare memory layout using scattergather list with pointers to data and metadata buffers. After that, we register signature MR using send work request with a new special opcode. And after registration, we can use SIGMR data paths instead of regular memory region. In the end, when our request which uses hardware float is completed, we need to invalidate used signature MR. About our plans, we plan to finish implementation of user space signature API this year. It will be based on Mellanox direct verbs provider. And after then, we plan to enable tit and diff hardware offload in SPDK. Next slide, please. Here we can see a comparison between software and hardware signature calculations. The chart shows preliminary results of read operation with Samsung disk. The SPDK target and initiator were run on a single core on 86 machines. As you can see, hardware calculation outperforms software by 200%. Next slide, please. And that is all that I wanted to cover in my part of the presentation. Thank you for your attention.
Thank you, Alexey. Any questions for Seth or Alexey? You can either raise your hand by clicking on your name in the attendee panel, so I can give you an opportunity to speak, or you can even submit the question using the Q&A panel in your WebEx window. Okay, I do know how to find Seth and Alex. If you have questions, please let us know. I'll follow up offline. The next is a break, but before I lose you all for a break, I just want to throw a few reminders in here. In the chat window, I put in a link for the Day 2 survey. Please use that hyperlink to provide any feedback you have on today's sessions.